Good afternoon and welcome to this afternoon's webinar, Water-Based Investigations, presented by Tim Gavin, Area Manager for Atlantic Testing Laboratories.
Hello, everybody. My name is Tim Gavin, Area Manager at ATL, with my primary focus is the management of our subsurface division, performing soil borings on land and water. But over the years, I've spent quite a few summers on our sediment boat collecting sediment samples throughout the Northeast. Webinar here is a water-based investigation webinar. It's going to have two main focuses, sediment sampling and geotechnical sampling. We're going to start out with the sediment sampling side of things here. So when we talk about sediment sampling, we are sampling for contaminant characterization, got a body of water and potential for a contaminant to be in that body of water, collecting surface sediments to see what is in there and if it is contaminated. Contamination delineation, collecting samples to see how far that known contaminant extends out into the body of water, how deep it goes. Environmental remediation design. Again, collecting samples to see if the plan is to dredge out 3 foot of sediment, what's going to be left, that below that 3 foot mark, is cap going to be necessary? Is it still going to be contaminated? Cleanup confirmation sampling. So come in and dredge or cap, confirm, taking sediment cores to confirm, to make sure the cap material was placed correctly, that the cap thicknesses are what they're supposed to be, and the material used for the cap is the correct material. And then dam rehabilitation. So, over years, sediment builds up behind dams, and you come in to do work on that dam. A lot of cases, that sediment's going to get disturbed and distributed downstream, and DEC requires sediment cores to characterize that material to know what's going to be spread downstream. For the geotech side of things, we're going to talk about what type of investigations are water-based investigations for geotech purposes, sheet pile design, structural design, dams, bridges, piers, boathouses, designing the foundation systems for those structures, and then to support remedial design, slope stability, capping, etc. If you put a cap material on soft sediments, what's going to happen, to that soft sediments? Is it going to slide? Is it going to shoot out in other areas of the bodies of water? So here's just a quick picture of a typical water-based setup. This right here is our 3-section barge with a geoprobe on the barge. That's used to take geotechnical samples. And then over here, on the right side of the picture is our sediment boat, where we collect Vivacor samples and sediment cores. Okay, so sediment sampling methodologies. There's a handful that we utilize here at ATL: Vivacor sampling, push coring, polar dredge sampling, and split spoon sampling. Could throw gravity core sampling in there. We don't really hit on that here in this presentation. So Vivacor sampling. Vivacoring is a sediment sampling technique used for retrieving continuous, so-called undisturbed sediment cores. There is a little bit of disturbance when you're taking a sediment core, but essentially it gives you a complete profile of the depth of core that you can visually classify what the different soil stratas are, and delineate where there could be potential contamination. So this is a picture taken from a job site actually down in New York Harbor. This is the Vivacor right here in the center. What that is just an electric motor that vibrates this long steel barrel into the sediment. Can utilize either a steel barrel, a polycarbonate barrel, aluminum barrel. We use multiple different styles of barrels. Each has their advantage and disadvantage. Typically, the aluminum barrels are one-time use. Core it into the sediment, pull it up, pull it off, cap it, and then take it for processing. You really can't see what the material is through the steel barrel or the aluminum barrel. When we're utilizing a steel barrel, we're putting in a polycarbonate tubing inside of the steel barrel, coring down, usually using a nose cone on the end of the Vivacor barrel. The nose cone has fingers on it that helps retain soil samples. And when we extract the core barrel out of the water, pull that core tube out of the barrel, and you can see the recovery and your soil classification is a lot easier with the polycarbonate tubing. So for our purposes, we're usually good up to 20-foot Vivacor length. Anything over that, we don't have the means to advance it. To advance a Vivacor, you need a crane or a derrick that is at least tall enough for your barrel to be supported on. The Vivacor is placed in the water with a winch cable attached to the top of it, and drop down to the bottom. It's typically best used in fine grained soils, and your silts and clays is where it's predominantly used for. It can be used in sands, but my past history have learned that in sandy material, you're usually only good up to about 10 to 13 foot of depth using the P3 Vivacor that we utilize. For whatever reason, the sands seem to compact inside the core barrel, and once you get past those depths, they no longer want to come up into the barrel, and you get a lot of resistance going down and lower recoveries. We have attempted 20-foot cores in coarse sand, but recoveries seem to be problematic when we're doing that. Couple important things to know when you're Vivacor sampling. Like I said, the Vivacor is put down with a winch cable to the sediment bottom. Knowing when that Vivacor hits the bottom is important. When the nose cone reaches the bottom and the Vivacor is activated, you don't want to assume that the Vivacor is on bottom and core through open water and then hit the sediment. So knowing the depth of water and how far your Vivacor is down is important. Getting the Vivacor in straight is also important. This is easy when the water's shallow and you can see the whole setup go down and Vivacor into the sediment. But when you get into the deeper waters where you lose sight of the Vivacor, it's important to have an experienced Vivacor operator that knows when the Vivacor reaches the bottom and knows to keep the tension on the cable so it goes in straight. Another thing to know, and an experienced Vivacor operator is important. When you're in rougher water, you have a tendency as the boat goes up and down in the water, the Vivacor could almost work as a woodpecker going in and out of the sediment, and you don't want to do that. You want to make sure there's enough slack in the Vivacor cable as the boat goes up and down with the wave action that it continues to core straight, and you're not recovering multiple sections of the 0 to 6 inch interval, make it look like you collected more core recovery than you actually did. All right, so the next methodology here is Ponar dredge sampler. Ponar dredge is what's pictured here on the end of the crane. That's really a surface sediment sampler. We use a standard Ponar, which is 9x9. We'll collect a 9-inch by 9-inch sample. So it's only going to penetrate into the sediment 9 inches and grab a bulk sample of that superficial samples or sediment. The way it works is there's a spring-loaded pinch pin that goes into the apparatus. So when you put it over the side of the boat to go down into the water, you got to keep tension on the cable as it's lowered to the bottom. Once that tension is released, that releases the pin and allows the clamshells to clamp into the sediment. I typically like to lower the ponar by hand, get a little more control with it, and you get less false activations. If there's any kind of jerking, when the ponar goes down, the tension will get released off the cable, and it'll prematurely activate before it gets down to the sediment surface. Couple problems with the ponar. You got to have the right sediment consistency. Gravelly bottoms are problematic. What tends to happen is when the ponar clamps down, if you get a cobble wedged in between the clamshells, it won't seal all the way, and as you retract the sampler up through the water column, it's just going to dump all your material. The same thing with sticks, have a tendency to get wedged in the sampler, and again, not allow it to close all the way. And then real dense material, the clamshells won't penetrate into dense material and essentially sit right on the surface. The next methodology that I'm going to talk about is push coring or manual sampling, predominantly used in shallow water, where you can't get the Vivacor boat in, or the larger drilling barges into. Got a photo here in a wetland, trying to collect some sediment cores for a remediation project. In this case, we're pushing what we typically do is we push the Lexane tubes that go inside the steel barrel, the polycarbonate tubes. We'll push them in, as far as we can go by hand, and then put a cap on top of them, tape the cap, and create a suction and retract the cores. It's definitely a manual process. It takes a lot of effort to make it work. Challenges are actually getting, typically pushing the core down isn't all that bad. It's getting it extracted out of the sediment. Once you put that cap on and get that suction, it's hard to break the suction, at the very bottom, to get that core sampler up and out. Other concerns that there are areas that we've seen problematic, especially in a wetland area like this where there's a large root mass. That surface 1 foot of root seems to be problematic. A lot of times we can push the core through that, but for whatever reason, that root mass will bind up in the sample and not allow the sediments below to come up in and get a good recovery. So what we typically try to do when we're doing push cores in an environment like it's pictured here is take a post hole digger and break up the first 6 inches to a foot of that root mass. So it's a little bit easier to push the core tube, and we tend to get a lot better recoveries, and just bag sample the that upper 6 inches to a foot. All right, so the last methodology that I want to talk about during the sediment sampling portion here is split spoon sampling. Split spoons are typically used for geotechnical purposes, but they can be used for sediment sampling as well. Where split spoons are advantageous versus the other sediment sampling methodologies is when you have a really hard bottom that you can't get the Vivacor to penetrate, or any other really sampling mechanism to penetrate. Your only option really is to drive a split spoon sampler. And split spoon samplers are typically 2 inches in diameter, but you can get them 3 and 4 inches in diameter. They're typically 2 foot in length for geotechnical purposes, but you can get them 4 or 6 feet in length. If you're strictly doing the sampling with a spoon sampler for environmental purposes and SPT data is important, you can go with a longer sampler. So essentially that split spoon is just driven, with a hammer down into the sediments. The softer sediments, where Vivacor is advantageous, the split spoon sampler is not. Typically what happens in those very soft sediments is that the sampler doesn't have a good vacuum, and the spoon sample retainer isn't designed for those soft sediments. So what usually happens is it will run out of the spoon as you're extracting it out of the hole. But then, your dense material, your dense sands and gravels, the spoon sampler might be your only option. Okay, so getting into now the geotechnical side of things, away from the sediment side of things, methodologies that I'm going to talk about a little bit are, again, split spoon sampler, but in this context for geotechnical purposes, not the environmental purposes, Shelby tube sampling, band shear testing, comb penetration testing, and subsurface investigation log review. All right, so spoon sampler. Again, that's done in accordance with ASTM-D 1586 when you're doing it for geotechnical purposes. You're using a 2-inch diameter split spoon, that's 2 foot long, driven 2 foot at a time. Use the sampler for soil classification. Soil samples recovered within the spoon for soil classification and for future geotechnical testing. When we're doing water-based work, we will not use hollow stem augers on a barge for a couple different reasons. We only use a casing, either spun in or drive and wash. So when we do geotechnical borings from a barge, we do it through a moon hole in the center of the barge. That moon hole is 6 inches. We can put 6-inch casing down through that moon hole to sample within, or up to 6-inch casing, I should say. Hollow stem augers are a little bit too big to fit down that. Hollow stem augers are generally heavier than the casing, and so stringing those augers through open water is somewhat problematic. There's a high risk of losing those augers as you are putting them down through the water column, through that unsupported water column. And then hollow stem augers are typically, unless you have a brand new set of augers, the joints are relatively loose. So getting a straight hole is very problematic when you're in a long water column. The joints tend to flex as you put pressure on them, and the augers want to walk. And once the augers start walking, they will start binding on the moon hole. So ATL will not use hollow stem augers, I guess, long and short of it, when we're doing geotechnical borings from a barge. We're going to use a case process, either driven or spun casing, depending on the circumstances. A lot of times, when we are doing geotechnical borings from a barge, it is through a contaminated body of water, and we have to implement double and triple cased holes. Essentially, what a double cased hole is, you put the outer casing, a larger diameter casing, down through the water column into the sediments. And typically the sediments at the surface are where your contamination is, and then put so you seal off that zone so you're not dragging contamination deeper down into your boring, down into uncontaminated zones. So you put a clean casing down inside that outer casing and advance your boring. And there is certain circumstances where we have to triple case a hole. That surface sediment is contaminated, but then there's another zone that's less contaminated, but still contaminated, but they don't want it to get more contaminated. So add a third casing there to seal off that less contaminated zone, and then again advance the casing down through the clean material to your boring termination depths. All right, so this is a picture of a split spoon sample. So the way a split spoon sample works, there's a spoon shoe and a spoon head. When the spoon is put together, so those are two sides of the spoon, splits down the middle. You mate those two sides together. You put the shoe on one end and the head on the other end. It locks it together, and again, it's driven to, typically 2 feet within the soil. You want to make sure, especially with water work, that the check valve assembly in the head is clean and operational. You have the tendency when the check ball is not functioning correctly to when you're extracting that spoon, washing your sample away. So it's very important to make sure that is clean and operational. The next method here is Shelby tube sampling. Soils in northern New York or northern northeast are not predominantly soft soils, but when you get into some of the waterways, that is where you find your softer soils, softer clays, and that's where Shelby tubes will come into play. A Shelby tube is an undisturbed sample collected in accordance with ASTM 1587. It's mainly used in your cohesive soils, your clays. What a Shelby tube is used for is to try to get the most representative of the in situ conditions of the soils, of those cohesive soils, and to run your more in-depth laboratory analysis on that undisturbed sample. So it provides the most accurate representation of the in situ conditions. Right here's a picture of your Shelby tube. Shelby tube advancement is the same whether it's in the water or on land. I guess the biggest thing with advancing your tube on the water is to make sure that it's stored correctly once it's extracted. Make sure it remains vertical at all times. Make sure it's sealed correctly with your wax seal and capped. You're on the barge. Barge is potentially moving around a little bit, going up and down depending on how rough the water is. So you want to make sure that tube is in a secure, safe spot and not rolling around the deck of the barge and disturbing that sample. Next method here is vein shear testing. Again, that's going to be in cohesive soils, that we find more in water work than we do on the land work here in the Northeast. Vein shear testing is done in accordance with ASTM D 2573, performed in cohesive soils, and you're determining the shear strength of the soil material in situ when you're doing the vein shear testing. These are typical veins. Depending on the density of the soil will depend on which vein to use. You want to use the bigger veins and softer material, and the smaller veins and more dense material. I think I got a picture. Yeah, here's a picture of doing vein shear testing in a wetland. ATL uses a mechanical vein shear testing equipment. It's kind of old school. It's been around for a long time. And so what you're doing is rotating the vein in the hole and determining where it shears by a force gauge, calibrated force gauge. In this situation, we use vein shear testing because we didn't have any other means really to get in situ geotech parameters in this wetland. We couldn't get a conventional drill rig into the wetland without a large sum of money to get it mobilized through the wetlands. So we chose to use the vein shear equipment to get the soil properties, geotechnical soil properties that we could get. So we pushed the vein by hand and set up the vane shear apparatus there in the wetland. Okay, the next methodology is cone penetration testing. And again, cone penetration testing on land is very similar to what it is in water. What cone penetration testing is it pushes a cone with electronic sensors that are measuring tip resistance, side friction on the cone, and the pore water pressures. It's done in accordance with ASTM 3441. This is your cone over here. It outputs to a computer. The advantages of CPT are that you can get a lot done in a hurry. It's not uncommon to get 200 to 400 feet of advancement within a day, depending on the conditions. So the CPT is very advantageous to get a lot of geotech information in a hurry. The setup of the CPT equipment is a little cumbersome. The electronic cables have to be strung through rods down to the cone. So the setup usually takes a little while, and the teardown takes a little while. But once you're set up, you can go through a lot of footage in a hurry. Cone penetration testing does replicate to some degree, what pile driving will do. Get your side friction and tip resistance. It's useful in cohesive or to some degree sandy soils types. Disadvantage of CPT, can't push it in dense soil. Essentially, what you're using the hydraulics on the drill rig to advance that CPT cone. You're not driving with a hammer. You're not rotating it all. You're just using the downfeed hydraulics of the drill rig to advance that CPT cone. Where it does get challenging on a barge, your counterweight is essentially the barge itself, and termination may be a little bit earlier on the barge than it is on land, because what typically happens, we get in the dense material, we'll start lifting the barge up out of the water, and potentially could cause it to shift on the spuds and cause issues there and break stuff off. So that is where cone penetration testing on water is a little bit different. Another disadvantage is no samples recovered when you're pushing CPT. You can't take soils back to the lab to do your more in-depth laboratory analysis on them. So all your soil classifications are based on the soil properties. When you're doing CPT on water versus on land, there's no way to do your seismic shear wave velocities. That's one thing the CPT on land can do. It can help you with your seismic site classifications. You can determine your shear wave velocities with the CPT cone. There's no way to do that on water. The way that the technology works, a steel I-beam is struck with a calibrated, as Adam Snyder, a geotech engineer that does a lot of CPT works, that a calibrated sledgehammer strikes the steel I-beam and sends a shear wave down through the soil to the CPT cone. There's no way to do that on a barge to get that shear wave through the water column to measure on the CPT cone. At least ATL does not have the technology to do that. Right here is a typical CPT log, what it measures. This one's actually on land. Not sure why I didn't put a water-based one on here, but anyways, it shows the tip resistance and TSF, local friction and TSF, friction ratio, pore water pressures. This over here so I can see a little better. And will give you an SPT range here. It's estimate and your soil behavior type. So it'll kind of classify your soils and based on what the soil properties are and give you a behavior type. All right, so here's some photographs of the CPT. As you see, this is time-consuming stringing that cable through these rods. It does take a little bit of time to do that. It's important to know how deep you're going to be pushing your CPT, because once they're strung, it's hard to string on more rods, or it's a little cumbersome to string on more rods. So essentially the CPT, when we're doing water-based CPT, we'll put an outer casing down through the mud line to give that CPT cone a little more stability as we start pushing it. And then there's a measuring wheel that's put on top of the casing that measures the depth as the cone is pushed. We do have CPT rods that we can grout through. So when we do push CPT cones in contaminated situations, there is sometimes the need to grout that hole up at the very end. We've had limited success with it. It's a small tube that goes within the CPT cone that has ports on it, and the volume of grout that we can get through that small tube, like I said, we've had limited success with it actually working the way it's supposed to. So the next section we're going to cover here is subsurface investigation log review. The boring log for water-based drilling is the same as for land-based drilling. The only difference is the water column and how you account for that water column on your boring logs. And done it a couple different ways. In this scenario here, we reference the barge deck as 0. And then we noted where top of water was, and then where the mud line interface was. So the first 18.5 feet is open air on the log, or open water, I should say, on the log. And then the sampling started at 18.5, which is at the mud line interface. We have referenced 0 as the mudline interface, so it's all dependent on what the engineer's preferences are when we're doing the boring log. The only challenge or problem with doing it the way we did it here with this boring log is you have to have accurate water depth measurements. In tidal water, the water doesn't stay at the same depth. It goes up and down with the tide, and so that 0 mark is going to go up and down with your tide. So you have to pick a zero time, and make sure that you're adding and subtracting that depth appropriately as you're advancing your boring. It's not so challenging when you're doing continuous spoon sampling. You're essentially adding 2 feet every time to your hole, and you know that if you were at 20.5 feet with spoon 2, you drove it 2 feet, and you're at 22.5 feet, and then you drive your next spoon sample, it's going to be 22.5 to 24.5. It becomes more challenging when you're going to 5-foot sampling, making sure you get your depths correct. Make sure your driller knows where he is in the hole. It's not always as simple as just measuring, from the bottom of the hole to the top of the deck. You have to account for where the tide is at that given time, because it's going to be potentially a different measurement. But on the boring log, I guess get in a little more detail here. You got your soil classification, your blow counts. When you're doing SPT sampling in accordance with 1586, you're counting your blows every 6 inches, and those blow counts are correlated in the soil density types, and you can get your, at the end of the day, get your bearing capacity for those soil intervals. You're taking your end values to do that. Your end values are your middle 2 numbers. Your 6 to 12 sample interval, and your 12 to 18 inch interval within that spoon, and then your soil recoveries over here on the other side. All right, so next topic we're going to talk about is mobilization, which is really important with water work, because you can't just drive a truck up to the parking lot and do your soil boring. So it takes a little bit more coordination, a little bit more forethought to come up with how you're going to get the barge in the water and get it to your boring locations. With any mobilization, the first and most important step is to do an adequate utility clearance. Just because you're in the water doesn't mean there's not utilities out in the water. Typically, they're marked pretty good on the shoreline with big billboards saying not to anchor or drill in these areas. But sometimes they're not. You want to make sure that you're coordinating with the UFPO markouts ahead of time. Make sure that the UFPO knows that the work is in the water, and that somehow we have to distinguish. It can't exactly go out and put spray paint on the water where the utilities are. Distinguish on the shoreline where those utilities go into the water, and then where they cross and go out of the water. It's very, very important. So coordination with the utility companies is important with water work, especially when there's known utilities in the area. Water depth is important. Too shallow could be problematic, and too deep can be problematic. Making sure you know what the water depths are going to be, where you're doing your operations, where you're launching your barge, how you're getting your barge from your launch point to the boring locations. Is there a dam in the way? Is there locks that need to go through? So very important to know that route. Our barges will draft around 3 foot of water. So we need a minimum of 3 foot of water to set the barge in the water and transport it to where we're going. Sediment boats are 18 inches generally speaking. If we're doing sediment sampling, we can usually get away with 18 inches, spend as little as a foot. But in that scenario, you're usually forcing the boat into where you're going and pushing the sediment out of the way with the pontoons, and the motor is spinning in sediment. So it's usually like at least 18 inches of water depth with the sediment boat. Topography is important. You got a project in the Adirondacks, you got a big gorge, you need to do water work in. How do we get down to that water? Did a project in the Adirondacks where it was a dam investigation. I had to essentially drag a john boat down a hiking trail to get down to the water to launch the boat to go out and do our sediment sampling. But the topography is important, and what the shoreline is, and how do we get down into the water. When we do mobilize our barge for geotechnical drilling, putting in a conventional drill rig on the barge, our barge comes on a flatbed tractor trailer in sections and is placed in the water, typically with a crane. So you need shoreline access for a flatbed tractor trailer and a crane to set up next to that tractor trailer that can reach out into the water to assemble the barge. Our 3-section barge is 16 wide by 28 long, and that crane has to be able to reach out past so 16 wide, you're going to be out 12 feet or so out into the water, greater than 3 feet for the furthest section. When we're doing work on Erie Canal or any of the canals, canal permits are required, and you need access to put sport boats in and out of the water. Shoreline access, as you're doing your work, where are we coming to shore each day? Where are samples being offloaded? It's one thing to put the barge in the water down a sheet pile wall that's 10 feet tall with a ladder, and assemble thing while the crane's there. But at the end of the day, when the crane's not there anymore, how are we getting samples up off the barge? Climbing up a ladder, carrying things is not really appropriate. So making sure where we're going at the end of the day is important. All right, so here's our typical mobilization setup. Our tractor trailer with the 3-section barge loaded up on it, and then the crane will pick each one of these sections off and place it in the water. That is the drill platform. So one of our conventional CME drills will be placed on that platform to advance the borings. And here's a picture, of the sections going in the water with the crane. Once those sections are in, they get pinned together with long pins to hold them together. Going a little too fast, I guess. A couple things to mention with mobilization and water depth. Our 3-section barge or 2-section barge is typically anchored with a spud system. Spud system's good up to around 30 foot of water depth, and then greater than 30 feet going into an anchoring system, which is doable, just more time consuming. Barge is a little less stable with an anchoring system versus a spud system. So just things to note. We can't spud in, if we're bringing, 30 foot spuds and, we get out to boring locations and it's 40 foot of water, you can't spud in. And if we didn't bring anchors, then we're in trouble. So making sure we know what our water depths are before we get out there. Okay, getting into a couple, different scenarios for difficult access. Picture here to the left is, excavator vibracoring. We have done this numerous times now over the years, where we use the bucket of an excavator to reach out into a body of water, attach the Vivacor via cable to the bucket, and advance it versus using one of the sediment boats or a crane on a barge to advance that Vivacor. The neat thing with the excavator, you get into a dense material that the Vivacor really isn't going so good down through. You can always, if you're gentle enough, give it a little nudge to keep it going and get a little bit further penetration. So the picture to the right here, we've also done a handful of times now, is tripod vibracoring. Can't get a boat into where we're going, water's too shallow. So set up the tripod out in the body of water and attach the Vivacor to the tripod and advance it down into the sediment. Time consuming process getting that tripod set up. This scenario, we hit contamination where we didn't expect to hit contamination and ended up having to do step outs. So moving that tripod 10 feet at a time to try to delineate how far the extent of the contamination is, that is kind of a pain in the butt to do, and time consuming and a lot of work. So prefer not to have to do step outs when we're doing tripod Vivacors. We have on occasion where we've had to get out farther into a body of water that we couldn't get a boat into, use the crane. Crane can get a little bit further reach than the excavator can. So we have had success attaching the Vivacor to a crane. Important piece here is to make sure that you have the right length Vivacor cable. Crane goes way up in the air and can reach way out. If you don't have enough cable, you got potentially you're gonna break that electric cable that's attached to the generator. So got to be careful of that. And then here's an ATV that we drove out into a body of water. It's actually up here near our office in Louisville. This scenario, bedrock was very shallow, which allowed us to safely drive that ATV rig out into the water to take the bedrock course for a new bridge pier. It was important to coordinate with DEC, make sure permitting and such was in place. We put turbidity curtain around the outside of the rig. We steam cleaned it before it went in the water to make sure there was no grease or oil on it. And the water got a little bit deeper than we anticipated when we got out there, and ended up having to disconnect the pulley to the fan of the Maruka carrier when we got out there, because the fan started slapping the water and we didn't want to shear off one of the fan blades. But all in all, it was a success. It's one and only time I think we've done that. So we have launched an excavator and a drill rig from our barge. We've used our 850 track drill rig to get to an inaccessible location along the canal. So tracked it off on ramps in that case, and in this case where we used the excavator to do some vibracoring work in this wetland. We had to use crane mats along the shoreline where it was soft to give us a little more stability, tracking the machines off the barge. Some safety considerations when doing water-based work. Coast Guard requirements. Generally, Coast Guard has guidelines on, what should be on your barge. We carry visual distress signals, flares with us, audible distress signal, blowhorn, fire extinguishers, first aid kits, eye wash. Make sure that we have those. They're up to date and on the barge and available if something goes wrong while we're out there. Generally speaking, and I think in New York now, everybody needs to have a boater safety class to operate a vessel on a body of water. We require all our operators to at least have a minimum of New York State boater safety class. We do have a handful of guys that are actually, licensed Coast Guard boat operators. So we do utilize them, on occasion. Life vests, we require our barges and our sediment boats are railed all the way around for fall protection, but we still do require everybody on the vessel to have a life vest at all times. Getting into the colder periods of the year, we switch from a life vest to a float coat, and then in the even colder periods of the year, we switch from the float coat to the flotation suits, the bigger Mustang orange flotation suits. Track the water temperatures and determine, different safety plans have different cutoffs there, but generally, 50 degree water temperature, you want to go to your float coat, and then, getting down in the 40 degree range, you want to be in your float suits. Doing water work, a lot of times you're on in contaminated areas. Advantage of doing work on the water. A lot of times it is cleaner when you're pulling up samplers through the water column. It tends to clean the sampler as you're going in and out. So it is a bit cleaner than doing work on land and contaminated soils, but still definitely have exposure to those contaminants. Occasionally Tyvek is required. Most cases you can get away with just wearing rain gear and deconning that rain gear at the end of the day. Out on the water, the elements are a little more pronounced. There's not a lot of shade. Hot, sunny summer day, real easy to get a nice sunburn if you're not protected. And then, with that being said, the wind blows a lot more out on the water. There's not a nice wind break typically on open water, so it can get quite a bit chillier when you're working out on the water. Drilling in general is using heavy equipment that does get suspended up in the air above our heads. Barges and sediment boats are constrained, not a lot of room on them. So full PPE is required while we're out on the boat. Hard hat, safety glasses, steel toe work boots. Got to be conscious of overhead hazards, stuff potentially falling. We did have a lesson learned early on in my career, 15 years ago. Guys were doing a boring out in deep water, had strung rods up through the tower and had left them over the weekend, had 50-foot of rod up in the tower, secured it through the hoop, but came back after the weekend and the top rod in the string had unthreaded itself and was just hanging at the very top there. Wasn't really threaded in, it was just kind of rested on the rod below. Just the wave action over the weekend had vibrated that rod enough that it had unthreaded itself, and became a little bit of a hairy situation. Everything ended up working out for us, but it took a lot of consideration before we determined how to get it down safely without it falling and hurting somebody. We have made it standard practice now not to leave any joints above the tower if we're going to string rods up through the tower and leave them, overnight. The 30 foot is generally the max that we'll allow. So there's no joints up above the hoop in the tower. I guess a note here is productivity is lower on the water than on land. Just in general, traveling up and down through that water column each time, to take your sampler, that adds time. So productivity rates are generally slower on the water than they are on land. The use of the auto hammer versus a safety hammer to drive your spoon sampler is typically what we want to do. Auto hammers are much safer than running the gin line and the cat head, especially out on a barge setting. Less likely to get the gin line caught up in something, less likely to lose your balance using the auto hammer. Crossing your gin line, rough water, trying to operate that cat head and cross your gin line, then the hammer goes to the top of the tower. There's nowhere to escape from when it comes crashing back down. So generally speaking, we like to use auto hammers out on the barge when we're doing geotechnical borings versus the old school gin line and safety hammer. Visitors on the barge are somewhat problematic. The barge space is limited. Keeping visitors outside our work area is more of a challenge. When we do have multiple people out with us, oversight with us, generally speaking, we like to keep them on the sport boat, not on the actual work surface where we're conducting our work, just because of the limitation in space and the potential for hazards associated with our operation. Unusual hazard recognition, low bridges, low power lines. When we are running our barges up and down a waterway, typically we're running with potentially 40 foot spuds in the barge that are all the way up. So that's 40 foot of steel pipe that's up in the air, and if you're going down along the river and there's a power line that goes across that river and power line's at 30 feet and you got 40 foot spuds, that's going to be problematic. So hazard recognition on barge work is very important. Knowing what your route of travel is and what those hazards are along your route of travel. All right, so Howard, I think we're getting into the test section here.
All right, I pushed the first one out.
Okay, first question. What are the end uses of sediment sampling data? Okay, answer there is D, all of the above. Environmental analysis, dredge depth and extent, dam rehab are all common areas that sediment sampling data is used for. Okay, next question. Which of the following is not a sediment sampling methodology? Okay, pretty straightforward. We hit on all these except for monitor well boiler, which I have no idea what that would be. True or false? Split spoon sampling is advantageous for gravelly, rocky bottom substrates. Coarse material. True, we did talk about that. Vivacor is typically not very good with the harder gravelly bottoms, and split spoon sampling is really your best option when you get into the denser gravelly bottom substrates. True or false? Vein shear testing determines particle size of in situ soil. That would be false. Not really. Vein shear is determining your shear strength. Okay, which is not an advantage of cone penetration testing? And that would be C, cannot be advanced into bedrock. CPT cone would hit refusal on bedrock. It does not core into it. So C is not an advantage of CPT testing. All right, what do we got for questions, Howard?